Hi, my name is Dr. Bridget Still, and I wanted to go over some examples dealing with probability. So here is what we're going to talk about. First, we're going to go over the definition of probability. Then I'll do some formulas and some examples. And then we'll have a nice summary at the end. So the definition for probability is the extent to which an event is likely to occur measured by the ratio of the favorable cases to the whole number of possible cases. Now that's a real complicated way of saying we're going to take the number of desired events divided by the total number of events. So let's look at an example. In a bag, there are 3 yellow, 4 green, and 2 blue marbles. What is the probability of choosing a green marble? So first we want to see how many total marbles we have. So 3 plus 4 plus 2 is our total number, and we have 4 green marbles. So that's going to give us 4 over 9. Another thing that's discussed is empirical versus theoretical probability. In theory is what you want to think about when you're thinking about what theoretical probability means. So if I flip a coin 100 times, in theory, I should get 50 heads, and 50 times it should land on tails. But if I actually did that, that might not actually be what happens. And that's what, when we say find the empirical probability, that's what that means. When you actually do the experiment, what happens? So, a die is rolled 300 times in an experiment. The results are shown below. What is the empirical probability for an even number? So, 2 happened 45 times. 4, 57. And 6 is 45. And this is out of 300. And so that's going to give us 147 out of 300, which is going to be 0.49. So the empirical probability of this happening is 0.49, but in theory, it should be 0.5. Another way probability problems are laid out is using frequency tables. So the table below shows a breakdown of workers at a business. What is the probability that a randomly selected 45 or older year-old is male? So first thing, it says that a randomly selected 45-year-old or older. So that is the only thing that we're going to be looking at. And then is male, so there are 125 out of a total of 225 people that are over 45. So that's going to give us 0.5, repeating. So we're going to put it 0.56. Let's look at another example of a frequency table. The table below shows a breakdown of workers at a business. What is the probability of selecting a worker aged 18 to 25 to the nearest hundredth? So, workers 18 to 25, there are 125 of them, over a total of 775. And that's going to be 0.16. Now, to figure out some of our probabilities, we're going to use a tree graph. So the times you want to use a tree graph is when you have something that has two options. So if they ask about having a boy or a girl, if you have questions on a quiz and the answers are true or false, or if you're flipping coins and you'll get heads or tails. So that's when you're going to want to use one of these tree graphs. So for this one, it says 3 coins are flipped. What is the probability of getting exactly 2 tails? So with our first coin, we can either get heads or tails when we flip it. And then to represent what we can get on our second coin, I'm going to break this heads up into heads and tails, which is saying the first coin is heads, then I get the second coin heads. Or I can get the first coin heads, second coin tails. And I'm going to do the same thing with my tails. So I can get tails heads or tails tails. So that's with 2 coins, but we're looking for 3. So I'm going to do the same thing. I'm going to break each one up into heads or tails. So this is saying heads, 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 then heads, heads, tails. So those are my first 2 possibilities if I have 3 coins. So I'm going to do the same thing. Now I'm going to actually write out what this tree is saying. So one possibility is heads, heads, heads. Another one is heads, heads, tails. Then heads, tails, heads. Then heads, tails, tails. All right, now pause it and try to finish making this list. You're going to do the same thing that I just did with heads, but you're going to start with tails. I said pause it. Okay, now that you're back, let's see what you got. So we're going to continue. We have heads, tails. Tails, heads, heads. Heads, heads, tails. Tails, tails, heads, and tails, tails, tails. So these are all of the possibilities for this scenario. Now, the question says exactly 2 tails. So, this has 2 tails, this has 2 tails, and this has 2 tails. So I have 3 out of 1, 2, 3, 4, 5, 6, 7, 8 possibilities. So far, the problems that we have done don't necessarily need some of the probability formulas that other questions will. So let's take a look at some of the formulas that you will need to use for the other questions. So the first thing we have to do is decide if the formula is independent or disjoint. So independent means that the 2 events can happen at the same time. Disjoint means that they cannot happen at the same time. So for example, it cannot rain and not rain at the same time. You can't win and lose at the same time. You can't be born on May 1st and May 2nd at the same time. So those are an example of disjoint events. Now let's take a look at it visually. So if I have a dice and I roll it, and the first thing that I want to label for event A is if you get an odd number. So in my circle A, I'm going to write down my odd numbers, which would be 1, 3, and 5. And then the event B, or the probability of B, I want to see the probability that I get a 6. So in my circle for my event B, I'm going to have 6. And then 4 and 2 do not fit in either A or B. So if you notice, I have 2 completely separated circles. There is nothing in the middle that is an odd number, and for me to get a 6. Now let's look at the second example. So for event A is to get a number over 4. So in my circle for A, number over 4 is 5 and 6. And for event B is to get an odd number. So in my circle B, I have 1, 3, and 5. Now again, 2 and 4 are not over 4 or an odd number. But now notice that we have this intersection. So 5 works for event A, and it also is included in event B. And so when we're thinking about things that are disjoint and things that can actually happen at the same time, you can think of this diagram. So 5 fits into both, where here we don't have anything that is in both. Okay, so let's take it one step further. Let's actually look at the formulas for an independent event. You can have it be something and something else. So what's the event that I can ride a bike and hula hoop? I don't know. Now doing that at the same time would be kind of hard. But let's pretend that that was a different example. Okay, what's the probability that I ride my bike to work and Susie rides her bike to work? Okay, that can happen at the same time. So when you are looking for those type of probabilities, you're going to have the probability of A times the probability of B, and our key word is going to be and. Now don't worry, I'm going to go through this chart and then we're going to do some actual examples. Now, that's when they're independent. Now remember, disjoint cannot happen at the same time. So if I say what's the probability that it's going to rain and that it's not going to rain, that's not possible. So the probability would be 0. So if you have two disjoint events and they ask for the probability of A and B, it is always going to be 0, because if we go back to our diagram, it is 0 because there is no intersection. They are not connected. All right. Now you can also be asked an OR probability. So for independent, our OR formula is going to be the probability of A plus the probability of B minus the probability of A and B. Now the reason that we are subtracting this is because there's an overlap. Let's look at our example again. Alright, so we are looking at independent events and then we're going to look at OR. So let's look at our second example. If I asked you, what is the probability that you can get a number over 4 or get an odd number? Go ahead and just write that down. And it is as simple as you think. Count what's in here over the total. I said pause and figure it out. I don't know why you're not doing what I tell you. Okay, so hopefully you have figured out the problem. Now, you probably just said, okay, so there are 4 things that can happen out of a total of 1, 2, 3, 4, 5, 6. Right? And we can always want to simplify, so that's going to be 2/3. Now, the formula tells us that we're going to do the probability of A plus the probability of B minus the probability of A and B. It looks a lot more complicated than it is. So the probability of A is that I can get an odd number. So I have 1, 2 out of 6. the probability of B is that I can get, the probability of A is that I get a number over 4. The probability of B is that I get an odd number. So that's going to be 1, 2, 3. So that's going to be 3 over 6. Now, if you add 2 plus 3, you get 5 over 6. But we know the answer is 4 over 6. I wonder why that is. Do you know? Can you figure out why we are going to have 5 over 6, but we know the answer is 4 over 6? Well, if you realize that we actually counted 5 twice, then that would be the reason why we have a number that's bigger than what we know the answer is. So we counted 5 with the A, and then we counted 5 with the B. So there is an overlap. And this overlap is the probability of A and B. So remember, 5 goes with probability of A and also the probability of B. So since we counted it twice, we have to subtract one of them. So when it says minus the probability of A and B, we are subtracting. So we have 1 over 6, because this 5 is one number out of the 6 total. And then we would get 4 over 6, which is 2/3. So that is the reason why when we have independent events, we have to subtract the probability of A and B. All right, now let's look at the OR formula for when we have disjoint events. So you'll notice we should have the probability of A plus the probability of B, but we don't have to subtract this like how we have to when we have an OR that's independent. Let's see why. All right, back to our Venn diagrams. Okay, so here we have they're disjoint because they're not connected. And so for our OR formula for disjoint events, it's just the probability of A plus the probability of B. So our probability of A, that we can get an odd number, is going to be 3 out of 6. And the probability of B, that we're going to get a 6, is 1 out of 6. So we're going to have 4, 6. And again, that's going to be 2/3. Now there's nothing to subtract. We subtracted for the independent, we subtracted the and because we counted this 5 twice. There's nothing to count twice. And so there's nothing to subtract. And so that's why that formula does not have something to subtract at the end. All right, so here we have to add one more major thing that we're going to have to consider. And we're going to have to consider whether the probability is conditional, which literally means something is going to be based on something else. So if that first thing is different, the second event will be different because the second event is based on the first event. So that's the condition part. Now these formulas, again, might look a little scary, but fear not, because we are going to do some examples. All right, let's roll into the examples. Oh, but first, I wanted to let you know that this slide is available as a PDF so that you can have all these formulas written down very nicely for you to use while you go through the course. All right, let's look at another independent and probability question. So when I'm given a scenario like this, I go straight to the question to see whether I'm going to have an and or an or an if problem. So it says, what is the probability for the die to be greater than 4 and the spinner to be odd? Which means I'm going to use the probability of A and B. which is the probability of A times the probability of B. And again, these can happen at the same time. That's why I know that they're independent. Then I go back and read the scenario. And the reason I do this is because sometimes the scenarios are super long, and I'll keep reading the scenario over and over again trying to figure things out that don't really matter. So I get set so I can go back and see exactly what I need. So in a game, a 6-sided die and spinner with 10 equal spaces numbered 1 through 10 will be spun. Side note, did you know that die is a singular for dice? I didn't know that till about a year ago. Anyway, the probability of A is that it is going to be greater than 4. So that's going to be 5 and 6. So I have 2 out of a total of 6 possibilities. And then times the spinner to be odd. So I have 5 odd numbers out of 10 total. So 2 times 5 is 10. 6 times 10 is 60. And we always want to simplify. So that's going to simplify to 1 over 6. Alright, let's look at another example. Going straight to the question. What is the probability that each of the 4 cards is a diamond? Now, you might say, well, I don't know if that's an and or an or. You can always rephrase it to say, what is the probability that the first card is a diamond, and the second card is a diamond, and the third card is a diamond, and the fourth card is a diamond? So, we know that it's going to be and. So recall, our and means that we multiply. It just so happens that this time we're going to have to multiply it by 4 times because we're doing 4 cards. So we have 4 cards are chosen from a deck of 52 cards with replacement. A deck contains 13 cards, each of spades, hearts, diamonds, and clubs. So we're going to look that the 4 cards are a diamond. So we're going to have 13 diamonds out of 52 cards. So that's the probability of drawing it the first time, or the first card. And then the probability of drawing a diamond second card is still 13 over 52. And again, this is staying 52 because we are replacing that card back. And then diamond the third card is the same. And a diamond the fourth card is the same. Yes, these numbers are going to be really big, and it's okay. So, if we multiply 13 by itself 4 times, we're going to get... And then 52 by itself 4 times. And that will simplify to 1 over 256. And when doing these problems, sometimes it's hard to tell if your answer would make sense, but you always want to ask yourself that. So thinking of the scenario, 1 out of 256, that makes sense, right? If you got 1/4, yeah, no. Okay, so just think about, does my answer make sense? All right, let's look at another example. The probability of a sunny day is 0.7, and the probability of the date on the calendar being an odd number is 0.5. What is the probability of the calendar date being odd or it being a sunny day? So now when we go to the question, which is the whole thing because it's just one sentence, we go and we're going to look for if we're going to have an and or an or an if. So it says of the calendar date being odd or it being a sunny day. So we're going to use our or formula, which is the probability of A plus the probability of B And these are independent events. They can happen on the same day, so we have to subtract that overlap. Okay, so the probability of A is that it's going to be odd. So it says an odd number is 0.5. And then the probability of B is that it's going to be sunny. And that is 0.7. And then we're going to subtract the probability of A and B. So remember, the probability of A and B, the formula, is the probability of A times the probability of B. And you can put that directly in your calculator just like this. Make sure that you use the parentheses, and that is going to give us 0.85. All right, let's look at another example. Again, I'm going to go straight to the question. What is the probability that he wears either a blue tie or a blue coat? So here you have the probability of A or B. It's going to be the probability of A plus the probability of B. And you can do both at the same time, so they're going to be independent. So you have to subtract that overlap. All right. So the probability of A is that he wears a blue tie. Now you want to be sure you are reading everything carefully because we are looking for a blue tie. So he has 2 blue ties and 1 red tie. So he has a total of 3 ties. So we have a total of 3 ties and 2 are blue. And then the probability of B is that he has a blue coat. So he has 2 blue coats and 2 orange coats. So he has a total of 4 coats and 2 are blue. A simple mistake that students sometimes make is they put the ties and the coats together, and so they'll say that there is a total of 7, right? But you're just looking at ties, and then you're just looking at coats. And then we're going to subtract the overlap again. The probability of A and B is the probability of A times the probability of B. And that is going to give us 5/6. Now the last couple of problems that we have done, we have had to find the overlap, meaning we have to do A times B. Some problems will actually give you, they'll say, the probability that they both will happen is this. And so if you do come across that problem, those type of problems, you want to use whatever they give you when they say both A and B are this. All right, let's look at another question. A game has a 10-sided fair die. What is the probability of rolling an even number or a number less than 5? So here is our keyword to let us know we are going to use our OR formula. So you have the probability of A plus the probability of B minus the probability of A and B. And again, I know that there is going to be something to subtract because I can roll an even number and I'll also be able to do a number less than 5. Now for these type of problems, I like to actually write out the possibilities. So we have 1 all the way up to 10. Okay, so we have the probability for A is rolling an even number. So let me put a star over my even numbers. And then the probability of B is a number less than 5. So I'm just going to underline my numbers that are less than 5. It doesn't say equal to or less than 5. It just says less than 5. So keep that in mind. All right. So we have 1, 2, 3, 4, 5 that are even out of 10. And we have 1, 2, 3, 4 that are less than 5 out of 10. And now we have to still subtract that overlap. So a star and an underline is an overlap. So we have 2 that are an even number and less than 5. So we have to subtract 2 over 10. Again, taking out that overlap so we don't count 2 and 4 twice. And that's going to give us 7 out of 10. All right, let's look at the next example. What is the probability of heading east and west at the same time? So, we have an and problem. And unfortunately on the slide I told you it was disjoint, but I'm pretty sure you would know that you can't go east and west at the same time. And so the probability of A and B happening is 0. Again, because you can't go east and west at the same time. So make sure that you are reading the question and determining whether it's independent or disjoint. All right, so the next question, it says the question, remember I go right to the question, what is the probability of winning or losing the match? So I have the probability of A or B. So I know you can't win and lose a match, so they're going to be disjoint. So I'm just going to add the probability of A plus the probability of B. So the probability of winning is 0.6, and the probability of losing is 0.4. So the probability that you're going to win or lose is 1, or which would be 100% because you're either going to win or you're going to lose. Now, say you still write down the independent disjoint or formula. You would subtract the probability of A and B, but there is no A and B because you cannot win and you cannot lose. So even if you write that kind of, just make sure that you keep in mind the scenario, and again, make sure that your answer makes sense. Because if you did something and got something besides 1, it really wouldn't make sense. All right, let's look at the next question. And I'm going to go straight to the question. What is the probability of drawing a 7 first and then drawing an even number second? So it's going to be an and problem. But it's going to be a little different formula-wise, even though we're technically going to do the same thing. So we're going to have the probability of A, which is the probability of drawing a 7 first. Now, the next one, because it says, and then drawing an even number second, this has to happen second. So, we're going to have the probability of B given A, which is the same thing as saying the probability that B is going to happen if A happens. So A has to happen in order for the next thing to work, or to find the probability of them both happening. So the probability of drawing a 7 first is 1 out of 10, and the probability of drawing an even number second, so 7 is an odd number, so that doesn't change how many even numbers are still in the deck. So we have 5 numbers that are even, but keywords, without replacement. So if we have 10 numbers in the bag and we draw 1, then there's only 9 marbles left, right? And so that is the main reason why it's conditional. So we're going to have 5 over 90, which simplifies to 1 over 18. So you're still multiplying the two. It's just how you write the formula is a little different, but no one actually sees the formula you write down. So that's just so you know the difference, but when you see and, multiply. All right, let's look at another question. I'm going straight to the question. What is the probability that the first song is by Drake and the second song is by Rihanna? Now, again, we have an and, but that second song is going to be dependent upon the first song. So our formula is going to be the probability of A times the probability of B if A happens. Another way you can think about it. So this bar, technically we say given, but another way you can think about it, you can say or instead of given, you can say if. So now let's read the question. Charles has 6 songs on a playlist. Each song is by a different artist. The artists are Drake, Beyonce, Taylor Swift, The Weeknd. I didn't know you spelled his name like that. Anyway, Calvin Harris. If you don't know who he is, you're probably too young. And Rihanna. Alright, he programmed his player to play the songs in random order, again, without repetition. Is important. So, now, the first song is by Drake. We have 1 out of 6. And the second song is by Rihanna. We have 1, but we don't have, they're not going to repeat. So we only have 5 artists left. So then we multiply that and we get 1 out of 30. Or we can simplify that by doing 1 divided by 30, 2.03. We move the decimal over twice to get 3.3%. So I went through those because depending on your multiple choice selection, they can ask for the fraction, the decimal, or the percent. So you need to know how to go between those 3. Okay, let's look at another example. Straight to the question. What is the probability to the nearest hundredth that the second marble is blue? Keyword if. If the first marble is white. Whenever you see if, that means it's conditional because something is based on if something else happens first. So, the probability of B given A, which for this example is the probability that the first marble is white, the probability that the second marble is blue if the first marble is white. So the formula is going to be the probability of A and B divided by the probability of A. And you might say to yourself, hey, this looks similar. We got the probability of B and A and B and probability of A. This is kind of like the questions we just did. And it is. It literally is the same equation, but this time we're trying to find the probability of B given A. The other time we were trying to find the probability of A and B. And so, same thing, but it's just written differently based on the information that the problem gives you. So this problem gives us a probability of A and B and the probability of A. And the ones that we did before gave us a probability of B given A and the probability of A. If that made no sense, don't worry. Just keep going. Okay, so the first thing is the probability of A and B. So our probability is going to be that the second marble is blue and the first marble is white. So it says the probability of drawing a white marble first and a blue marble second is 0.19. So that is going to go on the top. And then the probability of A is going to be that the first marble is white, which is going to be 0.33. And that is going to give us 0.57. And we are rounding to the nearest hundred, so that's going to be 0.58. Now you might say, Bridget, how do I know whether to put the 0.19 or the 0.33 on the top or the bottom? Think of it this way. First thing, we have this and, which is this and, right? So you have two things that are happening at the same time. That is going to go on the top. Another way to think about it is, remember, this is the probability of B given A, or the probability of B if A. So, if A, whatever follows if, goes on the bottom, because the probability of A is going on the bottom. So when you're doing these type of problems, always refer back to this presentation, and the more that you do, the better that you'll get. It's going to, like I said, seem a little crazy at first, but when you do a few, you'll realize it's really not that bad. All right, let's do another one. So, straight to the question. If she goes to the doctor's office, what is the probability that she gets an infection there? I want you to find that keyword that's going to tell me what formula I'm going to use. Which one is it? Correct. It's if. If she goes to the doctor's office. That if means we are doing our conditional formula, which is the probability of B given A equals the probability of A and B over the probability of A. Okay, so now we have to decide what goes where. So, remember, last thing I said was whatever follows the if goes on the bottom. So here it says if she goes to the doctor's office. If she visits the doctor's office, it is 0.3. So that's going to go on the bottom. And then remember, on the top, you're going to have and. So you're going to need for both things to happen. So the probability that she goes to the doctor's office, this and, is this and. So the probability that she goes to the doctor's office and gets a new infection while waiting is 0.05. And so, that gives us 0.16 repeating. And to say where to round to, nope. So we're going to just say 0.17. Alright, so let's summarize what we've gone over. So the first thing you want to do is decide if the question needs a formula. So the first questions that we went over, we didn't need a formula. We were trying to see the empirical versus the theoretical probability, and if you don't need a formula for the frequency table, the ones that we did at least, and for the tree graph. And then the ones that we do need a formula for was when we're looking if it is independent, disjoint, or conditional. So we want to decide if the question uses that and, uses that or uses the if. Remember, those are key words to let us know what formula we are going to use, right? And then you want to apply the correct formula. So again, a tactic that I use is I go straight to the end, read the question, write the formula, and then fill in what I need for the formula. And then we want to make sure that the answer makes sense. So always check your work, and that is all. So have a good rest of your day. And don't forget, it's a video, so you can always go back and rewatch. All right, bye.